So they wanted to tell something about hypergeometric functions and how they appear in CFT. To be precise, how to get them without almost without solving any equations. So so we want to say okay. So okay, so suppose that we consider we consider a four-point conformal block where one of the fields is degenerate. So we have some theta 0, and there is the degenerate field, maybe 5 to 1, for example. Z1 with 1 theta 1. Here is infinity and theta infinity. In principle, we found that this satisfies the BPZ equation. And so it should be given. Okay, so I forgot to say that here it is dimension theta 0, and here it should be theta 0 plus minus b over 2. Intermediate dimension is fixed. So it should be expressible in terms of f(1). So there are two such conformal blocks, and in principle, dimension of this four-point conform of the space of such four-point conformal blocks is 2. So, but it is extremely painful to just to write this equation and then to solve it. And if we consider, for example, the case of double algebra, it's not quite obvious how to write the analog of this equation in the general case. So here we can try to play another game. We can look at the asymptotics of these conformal blocks around around singular points. So first we can look at asymptotics at 0. So what happens when we go to 0? So this phi to 1 of z. So phi to 1 of z approaches the state theta 0, and this OP starts from, so it contains a prefactor like z to delta of theta 0 plus minus b over 2 minus delta of theta 0 minus delta of minus b over 2 times a state with shifted theta. This is precisely what is written, right? So let me actually call this conformal block by some a letter. Theta 0, theta 1, theta infinity, comma z. And if we substitute the definition of delta of theta, what we will get? We will get plus some corrections, plus something. So maybe let me write it like this. So this equals to z to q times plus minus b over 2 plus b over 2 plus minus plus b theta 0. One plus principal some coefficient. And this is a sum over plus minus some c plus minus 1 plus something. And this acts on the state theta 0 plus minus b over 2. So we see that there is some.
The dimension of E1 is delta of minus p or minus delta. Minus delta or plus delta?
Here, dimension of the resultant field is with plus, and dimensions of initial fields are with minus. So how to understand this? Because, for example, imagine that we get a vacuum state after this, and then this dimension vanishes, and these two dimensions coincide, and we should get the two-point correlation function, which is z2 minus 2 delta. So what wasn't this question? And okay. And another check that we can say that original that dimension of our field is 0, then these two dimensions should coincide, or maybe there can be some other test.
Like the relative sum is clear. The point is I never remember it. Like when I say I get dimension delta, it's like I get dimension minus delta.
The formula which one should remember that O delta of z, O delta of w is 1 over z minus w to delta. It is decaying. So dimensions are usually positive in all normal situations, and the correlators should decay with distance. Physical correlators should decay. Change the equation. So so what we see here that the action of this operator I can produce these two conformal blocks in the space of conformal blocks. Like there are no other options. And now we can look at the behavior of these conformal blocks in Z. Namely, we see that if we perform analytic continuation around zero in this Z, these conformal blocks have different monodromies. So let us draw some picture. So there is this sphere with three singular points: infinity, 1, and 0. And if we go around 0, and there is Z somewhere. So if you go around 0, then this conformal blocks with a plus and minus sign. Let me call them. Maybe I will just put plus and minus. They are functions of Z. And they map to maybe maybe it is better to write it as it's better to write it as a row vector. So so they map to at times such diagonal matrix. E to the e to the 2 pi I. So for plus it is with minus sign, minus 2 pi I b theta 0 plus 2 pi I b squared and here it is e to the 2 pi I b theta 0. Right? So this is precisely what follows from this formula. And so it's fine, right?
Okay, there should be also a 2 pi I, but
Yes.
okay.
Yes. So there is such a property, and but now now it becomes natural to ask what happens if we go to some other point, for example, to 1. So if we go to 1, then it is a natural. Then the natural basis for formal blocks will be those where when we consider fusion of z with this theta 1 field, and then with everything else. So at 1. So in this case, the nice basis for formal blocks is this one, and this will be as before theta 0. This will be theta infinity. This will be theta 1, and this will be theta 1 plus minus b over 2. This is phi to 1. And asymptotics of these conformal blocks will be of the same kind. It will be z minus 1 to q b over 2 plus minus b over 2 minus plus b theta 1 times something. And this is one statement. Another statement is that these conformal blocks are some linear combinations of conformal blocks around 0. So we can say that this row vector of these two conformal blocks plus this minus is equal to two conformal blocks at 0 times some matrix. And some matrix C C01. Because the space is two-dimensional, there is nothing else here. So and now if you ask about monodromy, if you ask about monodromy of these conformal blocks around 1, if we try to consider them as an analytic function, compute the analytic continuation, then it can be done in the following way. So we can say that maybe better to continue here. So, and let us call this n0. So if you want to compute this monodromy in the clockwise direction around 1, so let us call this n0 and 1. So if you want to compute this analytic continuation, well, we should denote this somehow. Let us denote it y of z. Denote this vector y of z. And maybe y0 of z, and this is called y1 of z. So we can first write that y1 of z, y0 of z equals to y1 of z times C01 inverse, and then perform an analytic continuation of y1. So y0 of gamma 1 z. So and this path is denoted by gamma 1, and that one is gamma 0. So it's path of analytic continuation. So it can be written as y1 of z times this precise matrix e to the minus 2 pi I b theta 1 plus 2 pi b squared e to the 2 pi I b theta 1 0 0 times c 01 inverse. So it equals to y0 of z times c01 on this matrix C01 inverse. And the same can be done for infinity. I don't know. It is interesting to compute the asymptotics in that limit. So basically, it will be a similar expression, but with some different shift in b squared. So don't know if to compute this. But no, let us compute. So so this is the origin around around 1 and around infinity, and have around infinity and have such conformal blocks z1 infinity 0. So here we will have theta infinity plus minus b over 2. And let us look at the asymptotics. So here it's theta infinity. So it will be proportional to z to delta of theta infinity minus delta of minus b over 2 minus delta of theta infinity plus minus b over 2. So it is z to q b over 2 minus plus b over 2. All right. So there it was plus minus, and z to plus minus b theta infinity, something like this. It's Also a good question, which continuation around infinity to call M infinity, but let us say that it is a continuation like in a clockwise direction around these points. So it is a counterclockwise around infinity. So therefore this so this matrix is M1. So matrix for infinity should equal to wait, is all this correct or not? So here here I missed one point actually. This dimension of b over 2 enters with a minus sign, and so this cancellation here does not happen. So we should have another term here, which is mm, which is b squared over 2, because it's b squared over 4 plus b squared over 4 coming from here and from here. So plus b squared over 2. Right, and this one should be correct. So if I now compute this m infinity, it will equal to c 0 infinity. And now this arguments of the exponential. So the first one is e to the pi I b squared plus 2 pi I b theta infinity 0, 0. And this one is for the lower sign, it will be e to the 3 pi I 3 pi I b squared minus 2 pi I b theta infinity. Well, so we have such three matrices. Actually, I should. So it is continuation in the opposite direction, clockwise. So I should have put opposite signs in this exponential. So here it is minus 3 pi I b squared. Here is plus. And so we have such three matrices, and now we can say that if we perform analytic continuation around all 3 points, 0, 1, and infinity, actually it is a bit hard to write the correct formula, but let me try. So yes, thank you. 0 infinity minus 1. So 0, 1, and infinity. So now let us try to perform analytic continuation along this contour. Like when we first perform continuation around 0, then around 1, and then around infinity. So it's always hard. So so we take our function and perform analytic continuation. So we denote it like gamma 0 acting on z. So it's like to go from this point to this one, and this result of analytic continuation is given by y of z times m m0. And now let us say that after this we performed another continuation. So we take this z and further move it along this second cycle, and then around around this loop around infinity. So the question is, should we multiply from, should we act from the left or from the right? So, no, we take some, let us think that we take some initial value of z and move this particular point. So maybe it should be written like y of gamma infinity, gamma 1, gamma 0 acting on z. So it should be equal to y of gamma 1 times gamma 0 I'm always lost in these notations. We can, but there is also always a question: what is the order? Is it m0, m1, m infinity? Mm, oh, okay. Let us just write that m0, m1, m infinity equals to 1. Probably it is correct, but the point is that one should always think carefully what precisely is going on, because it is easy to make some mistake. So let us say that y of gamma infinity, gamma 1, gamma 0, z equals to y of z. So 0 and 1 and infinity equals to 1. If they act from the left, then this product will be opposite. But I believe it's possible to write a correct formula anyway. So at this moment, there is one non-trivial check which we can do, that we do not fail in all this computation of exponentials. So one consequence is that determinant of m0 and determinant of m1 times determinant of m infinity equals to 1. So and actually, here we have determinant of this matrix is e to the 2 pi I b squared. Here it's again e to the 2 pi I b squared, and here it is e to the minus 4 pi I b squared, because of this minus pi I b squared and minus 3 pi I b squared. So there is some minimal check that we do not make any mistake. And so once we have this setting, we can ask the following thing. So here we obtained just one row, which is transformed by this monodromy matrices. But it is natural to consider the following problem. So it is natural to consider the equation dy over dz equals sum of ai over z minus zi from I equals to 1 to, let us say, n minus 1 y. And the a infinity is minus sum of ai's. Y is, let us say that it is 2 by 2 matrix. Yes, of course. So that this equation makes sense. So it's 2 by 2 matrix. And let us study the behavior of this y. So if we study the system around z, so if z is close to the I, and then the system tells us that dy over dz is ai over z minus zi y. So plus something. So it can be solved locally by y equals to z minus zi to power ai. Well, to be precise, we can multiply this y from the opposite side by some matrix. By some matrix Ci. And now there is a question: what is the asymptotics of solution of this system? So we know that if we go around if you go around point zi, so this is power singularity. It's called this C tilde. So with a computer analytic continuation, y of gamma I times z, it will equal to z minus zi to ai, ci tilde, ci tilde inverse e to the 2 pi I ai ci tilde. Right? So it's just a trivial observation that this function is not non-single valued around the I.
Yes. Why the condition that the sum of derivatives is 0?
It's the definition of matrix A at infinity. It's one way to think. Another way to think is to try to perform an inversion. So we live on CP1, so let us try to rewrite it as, let us say that z equals to 1 over double. Then dy over d 1 over w, maybe, no, how to write it better? So, well, let us write this as so dy over dz, no, dy over dw equals to dy over d1 over z, so it equals to minus z squared times no, not z squared. Let us write z squared minus 1 over w squared. Sum from 2n minus 1 ai over 1 over w minus z zi. So this now equals to what? To sum from 1 to n minus 1 ai over wzi minus 1. And now let us write it again as sum of residues. So residue at 0 at w equals to 0 is minus sum of ai's over w, and residues of all this guys equal to 2, 1, because we can say that it is so no, so hmm? Hmm? No, because a residue is placed at the point w equals to 1 over the I, and derivative of this in w is the I, but this equals to 1 over the I. And no.
Okay, yeah. No, but I was saying when W was equal to 0.
In principle, we can we can just say that so this equals so it is it is to check that this equality holds. So you see, when we perform this inversion to look carefully at the point infinity, we see precisely this minus sum of a's. But it's also easy. It's also possible to see in the other way. So we should consider the one form dz times this combination. And if you look at the limit z goes to infinity, coefficient in front of 1 over z is sum of ai's. So but if you switch, so it means that asymptotics of y around that point should be z to power a infinity. Z to, well, if we define a infinity in this way, it will be z to power minus a infinity. So, and since coordinated infinity is 1 over z, then it is the same. It is the same as for other points, right? Uh, that's fine. So
This also one can see from as a consistency condition from the OD by integrating that right slider on a circle enclosing all the singularities.
no, but
It's not a requirement of analysis that we can
no. What do you mean?
So, like, if I take the integral over a circle left and right hand side, that encloses all the singularities.
Oh, but one singularity is at infinity. Okay. Let us say that you take some circle and excluding all the singularities. So you are taking some circle which excludes all the singularities, right?
That includes all the ZIs.
Okay.
And in this way, I mean, by assigning an infinity, you basically tell me that the residue of infinity is the.
But what is the meaning of residue in this case? You cannot say that a solution of the system is y times the exponential of integral of this connection.
No, probably I'm not able to explain myself. But maybe you can't do that because you don't know, like, otherwise, like, single value analytic or not in general. Like, why we only have broken expressions such as.
No, no, it is clear because if we solve this system around any other point, then this right-hand side is bounded, and y in that region is a homomorphic function. So it is homomorphic everywhere except for singular points due to some standard theorems about ODEs, like we can bound the right-hand side by a kind of maximum value of this matrix and see that y is bounded. And it is also homomorphic because so d bar of this is also zero because this equation contains only z derivative. So it's some.
Indeed. That's what I was trying to say. That if you take, like, if I integrate around a circle the left hand side, I get zero because it's a derivative of something. No?
No, well, you integrate around what contour?
Contour that enclose every singularity.
Yes, you can do this, but how can you compute the right hand side?
No,
Why
I
is
know that the integral is to zero by the
Mhm.
differentiation. And I'm
Yes.
trying to say that the fact that infinity is minus the sum of all the others is a consistency. I mean, if you don't say that infinity is that is the sum of all the others, this we don't have solution or we have some pathological solution.
Now, here we are just defining who is A infinity. We don't have such point here, and we need to write that. Let us say that A infinity is this sum of matrices.
This is okay. This is like
We don't have
assuming
choice.
the covariance of the equation when we change the coordinates.
Yes.
Okay.
Yes.
Yeah. Okay. Yes. And that's what I was trying to say somehow. That if we don't assign that condition, like the equation will be inconsistent on P1.
No, but inconsistent with what?
I mean, you cannot extend to infinity. I don't know.
No, we can solve it around all these points and extend to infinity and see some asymptotic there.
Yeah, but if I insist that infinity is not equal to the sum of all the others.
No, but you just see what happens with this solution at infinity.
Okay, so we can see in other terms. I can think. I mean, I can make this equation covariant around infinity by transformation law, and they say that A infinity is that. I mean, it's another way of saying the same thing.
Oh, maybe a little bit more productive observation in the following, so that we have some trivial statement. So if we ask if infinity is zero, then y at z goes to infinity goes to some constant. It's regular. It's homomorphic there. So this is a little bit so it is some a statement. It should be checked. Namely, when z goes to infinity, and this we call this a of z. This a of z behaves like 1 over z, like some c1 over z squared plus c2 over z cube plus, or maybe some b1, b2. And if you want to solve this equation dy over dz in that a limit, we can write that dy over d1 over z equals to minus b1 plus b2 minus b2 over z minus and so on times y. And this this bracket is bounded when z goes to infinity, right? So this is
Or one can also infer this from the form of the differential equation.
but it's no, but it's precisely what follows from the differential equation. So if sum of ai is 0, then expansion of this sum of first order poles starts from 1 over z squared. There is no residue at infinity.
But this is prescribed. I mean, when I have an equation of this type, okay, this is telling me that the residue of y around zi is precisely ai.
No. What is a residue of y? Y? It's a multi-valued function. So like z to some complex number, z minus zi to some complex number
And we were speaking about residue, so residue of what?
of a.
But no, but I was saying like from how it transforms the equation, like after blackboard,
Mm-hmm.
like when I set y going to 0, I see that the
Who is y going to 0?
the y w
Mm-hmm.
going to
Yes.
0. I see that this
Yeah.
is it's telling me that the derivative around is like something constant and something linear term, and when I integrate
Yeah.
it, I get
Yes.
something of this type.
Mm.
Okay.
But the point is that solution of such equation without singularities is holomorphic. So at z goes to infinity. Mm.
But I still have singularities, like I still monodromies around the other points.
Yes, of course, but not around infinity.
Okay.
So the only statement I want to make. Mm. Okay, so let me maybe erase this the statement around about infinity. So, so we see locally that this solution is multiplied by some matrix which is conjugated to e to the pi I ai, and uh, 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 well, it was just a solution around for one term, and we can ask what is the full solution of the full system, what is its asymptotics. So since it should be transformed precisely like this, uh, after the analytic continuation, then all the dependent part should be added from the left side of this term. And it is also convenient to say that this matrices are conjugated to some diagonal matrices with diagonal entries. So AI is equal to some G i's theta I 1, theta I 2, 0, 0, G I inverse. And monodromy matrices are also conjugated to exponentials of this thetas, but with some other matrices. C I inverse e to the 2 pi I theta I1 e to the 2 pi I theta I2 0 0 Ci. So if you have this, then asymptotics of solution around z goes to zi it can be written as some 1 plus z minus zi times something and so on times gi z and we call this matrix theta I, maybe big theta, z minus zi to power theta I times ci. So, but so is it clear? Hmm?
GI is still the constant matrix.
Yes.
What is a term in front of the
Because it is a solution of the full system, and because there are some other terms here. So if you wanted to satisfy this linear system, we should have.
that one is just the one.
Yes.
So that in the I you expect some constant matrix plus something in between.
No, no. Ci is a constant. Ci tilde is constant matrix. It's actually so in this notation it is something like C times G or G inverse. the CI is CI tilde is GI times CI. Oh, if we add something from the right, if we make this matrix z-dependent, then we will break this property that analytic continuation of y is y times some matrix on the right. And this was the property of initial system, that if we multiply y by some matrix from the right, it will still be a solution. So if you perform analytic continuation around some singular point, solution should map to solution. And so it means that it should be multiplied from the right, because if you multiply it from the left, it will conjugate the matrices of system. So it means that we can only multiply from the left, and so solution looks like this, right? So is it fine or not? Let me think. Maybe no, because we so when we compute when we apply this linear system, A's have G on the right, G inverse on the right, and it multiplies this G, so they cancel, and we get an access to this to this power. So.
If I have like that asymptotic solution around CI, and I do like the power series of C to the AI.
Z minus I to I.
And then is a diagonal, then we should conjugate with the G inverse on the right hand side, no?
What do you mean? So
if I have e to the
what?
Suppose I take the exponential of a matrix.
Of which matrix?
A.
A of Z or AI?
Since now it is diagonal, this is GI, the diagonal may.
Oh, of course, GI times e to the 2 pi I theta I GI inverse.
Exactly. Okay, so why now on the right hand side of y of z I have CI?
Because we can have arbitrary matrix there, and it will still be a solution.
But
and we had some.
is not the CI of the monodromy.
No, why? Monodromy.
No, because you use the same letter, that's why I was confused. It's not the same C of MI.
So it was C tilde, and it is C.
MI as a CI.
Like the matrix that conjugates the diagonal form of the monodromy.
No,
doesn't matter. I
understand. Oh, so MI will be given by CI inverse e to the 2 pi I theta I CI.
What we are saying is that the CI of the monodromy, that CI that you have just written, is a different matrix from the CI that is.
No. In what sense it's different?
Is it the same?
Of course, because if you compute analytic continuation around the I, you will get e to the 2 pi I, which appears on the left of the CI. So and if you multiply by this mi, you will get precisely the same. So this mi is a result of pooling of this prefactor to the right. So if you take, it's okay, right?
Yes.
So so yes. So what we have now, we have some number of these matrices A1 and so on an. One of them is infinity, for example. And we have matrices M1 and so on, Mn, monodromy matrices. Also, it makes sense to consider all these matrices up to the conjugation because it is just a change of basis of solutions, or it's some gauge transformation of the linear system. So if you consider these matrices with sum of a's equal to 0, factorized by what maybe PGLN 02 acting by so this is conjugate. This is the group of conjugations, and we can take a linear system with such matrices and compute its monodromies. So, and this is described by monodromy matrices M1, Mn with a product of mi's equal to 1. And this is can be again considered up to PGLN 02. So if you do this, we can call this monodromy map. But we see that dimensions of the spaces is the same in general position. We also fix. We can also fix eigenvalues of this AIs. So AIs should be proportional to theta. Should be conjugated to theta i's, and this mi's should be conjugated to e to the 2 pi I theta i's. So, and we can ask for solution of different problem, like how to recover original system if you know all these monodromies. And this is called Riemann-Hilbert problem, well, one of possible Riemann-Hilbert problems. But so I will talk about this later when we come to isomodromic deformations and the application of CFT in that case. But now let us try to apply this all these formulas to our problem. So. Namely, what I propose to do. So, we can ask the following question. So how many parameters are there in the system for 3 singular points? So let us compute the dimension for, so let us put n equals to 3, and let us compute the dimension of the space. So we can notice that since since sum of AI is equal to 0, sum of traces of AIs should also equal to 0. So sum of traces of AIs is 0. So sum of traces of this cetas should equal to 0 as well. So and if we ask for something else, then the solution, then we will not find anything like this space will have 0 dimension. So if we impose this condition, then we can switch to traceless matrices. So AI tilde equal to AI minus 1/2 trace of AI. So they are traceless, and we are looking for a dimension of space with I given by matrices A1, A2, and A3, such that some of these AIs, so they are in SO2. Some of these matrices equal to 0, and this is factorized by SO2. And also each of AIs is conjugated by conjugated to some diagonal matrix, so the eigenvalues are fixed. Yeah, tilde. Yes. So it is.
Ah, no, okay. Yeah.
Mm-hmm. And so the trace part easily decouples from any equation, because the identity matrix is commutative with everything, and we can write that y is some product of z minus zi's to a power of 1/2 of trace, and times some matrix of determinant 1. So we can represent A of z as a traceless matrix plus identity matrix times sum of poles with such residues. And is it clear?
No, sorry, can you write it down?
So yes. So a dy over dz can be written as sum of AIs over AI tilde or z minus zi plus identity matrix times sum of 1/2 of trace theta i's over z minus zi times y. And if we now introduce, if we now write that y is equal to a product of z minus zi to power 1/2 trace theta I times y tilde. And then this y tilde will satisfy an equation with traceless right hand side with traceless connection matrix. Yeah, thank you. Is it obvious?
Yeah, but in order to do so, we actually need the not the differential equation. Okay. Now we have like an n equals of matrices, which I know their sum is zero. So in particular, the sum of their trace is zero. But I mean, in general, I can like this transformation to reduce to traceless matrices, I can always do, right?
Yes.
So I mean, I don't need the condition that the sum of all AI is equal to zero, right?
No. Even if you have three traceless matrices, their sum should not necessarily be zero.
No, yes, indeed. What I'm saying is that if I have, I don't know, now is a simple condition, but in principle, I can have like any linear equation, let's say. I can always pass to solve the problem with traceless matrices.
Yes.
It's not really, I mean, it's to say, it's not like dependent on the form. Okay.
Yes. Yes, we can solve separately the problem for traces. It is trivial, and switch and consider only essential part, which is traceless.
Okay. And another question. So once we reduce the problem from all matrices to the traceless ones, why the conjugation change from PGL to SL?
It's the same actually. So I don't know. We can write. So let me think. No, we could write a cell from the very beginning, I think. Yeah. So. Yes. Yes. So uh, I, I don't know. I don't remember precisely what are the variants of this this group. So there is a SLN, there's PGLN, and probably there's something in between which contains factorizations by some parts of traces. Right? If you ask about groups that have algebra SLN, right? Probably. So PGL is when we factorize by the whole trace, by the whole center. But if we consider adjoint action, then all these groups are isomorphic. And after this.
So it's like basically it would be the conjugation by PGL because we are not caring about the determinant, but basically we choose just the one with the determinant one as a representative of this conjugation.
Yes. Okay, so now about the dimension. So we have three matrices in SO2. So it is 3 times 3. Uh, we have uh, uh, three conditions, that sum of them is 0. We have then three conjugations by SO2. And we have three equations for three conditions for the eigenvalues. Minus 3, so and it equals to 0. So dimension of this manifold is 0, and the same for monodromy matrices. Right?
Question, but can you associate those spaces of matrices Riemann surfaces?
Oh, but what kind of Riemann surfaces do you want?
I don't know. This seems like no, because like I was wondering before when you were speaking about monodromies at one point. It's really similar to when you have hypergeometric surfaces and you see them as a sheet covering of the plane, and you have monodromies around point that switch the sheets, and you say, okay, continuity is regular, not regular. And I was wondering if like those are actually surfaces because are defined by some polynomial equation.
No, but no, so those monodromies were just permutations. So we will talk about this when we come to twist fields. But that monodrome is so if you now try to say that there is, for example, some function such that mm, oh, how to say it. So you can try to define, for example, this object, to define some vector of functions in the following way. So suppose that we have some function which is defined on the Riemann on the Riemann surface, and so it's globally defined single value in the Riemann surface, and then try to define locally functions like we take n preimages or maybe two preimages of some point and say that first function is the first value, the value at the first preimage, second function the value at second preimage. And when you compute analytic continuation of this pair of function, you will of course get some permutation. But in our case, so this monodromy matrices will be just permutations. And in this 2 by 2 case, there is no such an interesting example because if you have three permutations, that their product is 1, it means that one is trivial, two other permutations are just transposition. So
But this would be like this kind of a sphere with singular points.
actually with two, because one is trivial.
Yeah, what I'm saying is like, I mean, this is a 2 by 2, so it's always a two sheet covering of something. When we do monodromies, we always swap.
No, if you want to consider something hyperelliptic, some cover of this kind. but for example, in the hyper.
If I just raise the number of points around this area of monodromies, even if I have just two sheets, I mean, I can obtain a more complicated situation.
Yes, you can, but the difference of that situation from the generic one is that square of that monodromies will be 1. If you go twice around this branch point, it will go back. So.
I mean, you mean in the case of what?
Of hyperelliptic covering. Yes. And we will actually see such example in CFT. So it really makes sense to consider such restriction on this thetas so that monodromy matrices become permutations or quasi-permutations. It's when they are multiplied also by some diagonal matrices. It is a perfect problem. We can write some explicit solutions in that case. But in the generic situation, these matrices are just some complex matrices, and the covering surface in this case will be the universal covering of a sphere with n marked points. So in this case, it will be upper half plane and upper half plane and this factorization map, which gets back to 3-punctured sphere, will be factorization by. So it is this. No, it is a little bit bigger group because this is the fundamental domain for SL for PSL2Z, and in this case we should get this fundamental domain with 3 cusps. So probably it's some gamma of 2 probably, right? I forgot precisely the name. Probably gamma of 2.
Maybe it's to early classification. What the universal code? I mean, you always get something which is simply connected.
No, because the question is what is the space where this function y of z will be single valued. So if it was covered with permutational matrices, then it is enough to take a double cover. So it will be a function and the analytic continuation of it. But if there are no algebraic relations between these monodromies, if there is a free group with 2 generators like M0 and M1, then the minimal space where this single value is a universal cover. Yeah, but what we see here that the dimension of the space is 0, and it means that these 3 matrices can be recovered just from their eigenvalues. So if we ask, so if we want to write them explicitly, we can write some expressions depending on thetas. And so maybe I can erase something in this one. So and also, so we know that on this this row of conformal block has three monodromes, M0, M1, and M infinity. By the way, the same is true for monodromies, that if we fix eigenvalues of each of the three monodromies, then they will be uniquely fixed up to the conjugation. So now we can try to check the following. So let us take a solution of this Fuchsian system. With y of z such that its monodromes m0, m1, and m infinity are the same as for this conformal block. Probably erase this function as for this conformal block. Theta 0, theta 1, theta infinity. Let us write the definition that no. We take such y of z, and now let us consider the following object. This row vector times y of z inverse. We have a guarantee that this is now a single valued function. So right. Because just because monodrome is one monodrome is act here from the right, another here from the left, and they cancel. And we can if we fix monodromes, then we fix exponentials of this thetas, and we still have asymptotics at this singular points. If you fix asymptotics accordingly, then it becomes holomorphic. Because this single valued function can only have poles at at the singularities, but if we look at the present apparatus d minus zi and ask them to be the same in this matrix K, and in this matrix case, and for our conformal blocks, then we can achieve achieve homomorphicity at this points. So we get some single valued homomorphic function on a sphere, and so on this expression, on this conformal blocks times of the inverse equals to some matrix C. Some row vector, right? A1, A2. Which means that if you want to get expressions for these conformal blocks, we should take a solution of 2 by 2 system with prescribed monodromies and asymptotics, and then take its first its first row, I think, right? Oh. Hmm? And no, only homomorphic functions are constants. Mm-hmm.
Okay, so those are constants only if we set like the sum of all the AIs to 0, basically. Right?
Of which AIs?
The one of the Fuchsian system.
No, but what do you mean? We are looking for a solution of the Fuchsian system with three singular points, precisely with this points 0, 1, and infinity.
Yes, but I mean, if the monodromy is like M0, 1, and M infinity, they satisfy that their product is 1, right?
Yes.
This automatically means that the function is holomorphic at infinity, right?
Which function?
Like the product of this.
This, right?
Yes.
No, in principle, we should care about asymptotics at infinity because we can have some pole there.
But we cannot because the sum of all the AIs in the Fuchsian system is 0. And before we said that the sum of all the AIs, but this didn't imply that the solution was holomorphic at infinity.
We should care about asymptotics at infinity because in principle we can have we can shift theta at infinity by some number. So it might happen that one
Yes, but at most this changes the value of the but it is like I mean I have like basically the only thing that changed is that those A1 and A2. But independently, if I even if I don't fix the asymptotics, I'm gonna get something basically, which is constant. Like I have a family of solution for all possible constant at infinity.
Oh, I'm saying that in principle, at infinity, one asymptotic that can have at infinity is this. It is z to theta z minus theta, for example, for SO2 case. But we can have as well z to uh, mm, uh, theta plus 2, z to minus theta minus 2. We can have such kind of asymptotics, and around any singular point. So this is what I mean by we need to fix asymptotics.
But we fix the asymptotics mean you fix the monodromies around each function,
Mm.
or you fix the monodromy at infinity.
No, fixing monodromy is not enough to get a homomorphic function. If you fix monodromies, we fix the values of e to pi I theta, and in this way we get some single-valued function, some single-valued function. So this one will be single-valued.
Yeah, that is single valued because they have the same monodromy.
Yes.
Cancel.
Yes.
Now, we said we need to fix the asymptotic at infinity.
No, around each point.
Around each point, not infinity.
No. Also, no. Let me think. If
both the function are regular at infinity, right?
so
The block has a singularity.
well, in principle, yes. Let me think. Oh, yes, it is true that if you fix asymptotics at 0 and at 1, then infinity will be for free, and because we have some matrix with a determinant of 1, and if it does not have but now it's not a matrix, it's just one vector, so mm, mm. If we are unlucky, in principle, we can get z, I don't know, z squared at infinity. Let me think. The question is, should it come with z minus 2 or not? Don't remember. Maybe after all it is true that it's enough. No, wait. No, it's not enough because we have three thetas and we should choose them appropriately.
Yeah, no,
Because
I think I misunderstood because like this claim, like what I'm saying is what I was saying is like if an is the sum of all the other, then it's regular. But this is like tautological in some sense because we are already saying that case that there is no monodromy.
no, we want monodromy at infinity because it is more convenient to choose points as 0, 1, and infinity. So there is no monodromy like in some other point. I don't know. So
Okay.
okay. Oh, it's already 6. Let me maybe finish quickly. So we see that this row of conformal blocks can be expressed as some combination of the elements of solution of this 2 by 2 system. And we know that this system is uniquely defined by three asymptotics at three singular points. And so the only question is what is the system and what is its solution. And to get this, let us write who is a hypergeometric function. So like this function, a, b, c, and z is a sum of, so it is 1 plus ab over cz plus a plus 1, b plus 1 over c plus 1, 2 factorial, z squared plus and so on, a n b n over c n, and factorial z to the n. So the series with the unit radius of convergence. So we can and so there is some good operator which is d over dz. So it is called theta. Maybe theta is used. Let us call it d. It's z d over dz. And let us see why it is nice. Because if we consider, if we take the combination a plus z d over dz, a plus d acting on f21 will equal to sum of just look at this term, at the second term. It will give a plus 1, a plus 2, b plus 1 over c plus 1 factorial z squared plus and so on. So we conclude from here that if we remove this a, it will give the same term, but for hypergeometric function of a plus 1. Of a plus 1, b C, Z. The same for B. And now let us do the same for C, but here we should take C minus 1 plus D. And this will give, so this will cancel this last C, so it will be A plus 1, B plus 1 over C 2 factorial plus and so on. Oh, sorry, here I forgot to write A times hypergeometric function. Here it will be equal to so let me see. So it decreases C by 1. So we are missing. So we can write it as C minus 1 times here C minus 1. So it equals to C minus 1. Hypergeometric function of 1 A B C minus 1 Z. So there is this relation, and now the last relation. So is it fine? Probably I can erase this part on the blackboard. We can notice that if we just take derivative of the hypergeometric function, so let us consider the following: d over dz f to 1. It equals to ab over c z plus ab over c plus a plus 1 b plus 1 over c plus 1, and here is 1 factorial z plus and so on, and it is easy to see that it is ab over c f to 1 of a plus 1 b plus 1 c plus 1 z. So it's a shift of all variables. And if you now take all these equations together, we can do the following. We can first act with this operator. So c minus 1 plus d on, so let us take d over dz, c minus 1 plus d times f to 1 of a, b, c, and z. So it will be what's c minus 1? It will be c minus 1 d over dz f to 1 of a, b, c, c minus 1 z. Alright, and when we take this derivative, then we use this formula. So we get AB f to 1 of a plus 1, b plus 1, c, z. Okay, and on the other side, we can act with this two operators a plus d. So if you write a plus d and b plus d on f to 1 of a, b, c, and z, it will be a, b, f to 1 of a plus 1, b plus 1, c, and z. So I'm now comparing these two formulas, and we get that a plus d times b plus d f to 1 equals to d over dz c minus 1 plus d f to 1. And now so it satisfies this kind of equation, which can further be written as so it is equivalent to z, like a plus d, b plus d equals to d c minus 1 plus d f. So, or if we open this brackets and collect powers of d, then we see that it is z minus 1 d squared plus what plus 1 minus c d plus z a plus b d and plus a b z f to 1 equals to 0. So this equation allows us to express d2 of f to 1 in terms of f to 1 and d of f to 1. So it's kind of demodular relation. So if we now consider the column vector consisting of f to 1 and df to 1, then a derivative of this will be equal to d over dz will be equal to what? So it will be equal to who? Where? because D is ZD over Z. So this is just a second component of this this common vector, and if we write this one, it will be 1 over Z D2 of F21. So let us continue here. Let me check my program. So now let's use this demodular relation here. So d over dz f21 df21 equals to 1 over z df21, and here it is 1 over z 1 over z minus 1 z minus 1 d minus z a plus 1 df. We just write f a plus b f minus ab f. So it's 1 over z df, and let us expand it as sum of residues. So 1 over z is equals to 1 over z minus 1 minus 1 over z. So this is z minus 1 over z minus 1 df minus c minus 1 over z df. This one is just minus a plus b over z minus 1. It was a b z. No, sorry, it was d here. It was df minus ab over z minus 1 f. So finally, we see only some linear combination of this f's and df's, and if we write this, we find that there is some matrix at 1 over z. This matrix is what? It has element 1 here, then it is element 1 minus c here, and it also and maybe that's all. Then we have matrix 1 over z minus 1. It has this form, z minus 1 here. C minus 1